In today's video, we're gonna talk about the epoxidation reaction. Before we get into the reaction, let's talk about the epoxide. So what is epoxide? Well, that is the cyclic ether with a three-membered ring. Let's take a look at some examples. So for the first one here, we have diethyl ether, which is a acyclic ether. We have another example here. Now we have a ring structure. And this one we call it a cyclic ether or an epoxide. So as you can see, we have a three-member ring here with one oxygen and two carbons. So we have a three-member ring. And the cyclic ether with three-member ring, we call it epoxide. The most important property of epoxides is they are good electrophiles and they can undergo SN2 nucleophilic attack. Let's take ethylene oxide as an example. So this is a three-member ring and it's a strange structure. Also, the oxygen is electronegative, so the oxygen is gonna withdraw the electron toward itself, and it gonna have a partial negative charge on oxygen, and we have partial positive charge on the two carbons. So we have partial positive charges on carbons. These two factors make an epoxide as a good electrophile, and it can undergo SN2 nucleophilic attack by a nucleophile. So with that ethylene oxide, so we know that we have a partial negative charge on oxygen and partial positive charge on the carbon. In the presence of a nucleophile, the nucleophile will attack the carbon and the bond between carbon and oxygen will be broken. So we're gonna form this intermediate with a negative charge on oxygen because the oxygen is a electronegative atom. It's gonna take the electrons of the bond between oxygen and carbon when the bond is broken. And with the acidic workup, we're gonna form the final alcohol product. So this is a typical reaction of epoxide, the nucleophilic attack. And so, what is the epoxidation reaction? Well, this is the reaction we use to make the epoxide. Let's take a look at the example, the reaction that we're gonna do today. So we have the reaction between cyclohexene and the metachlorobenzoic acid. And we're gonna form the epoxide as a main product. And we have metachlorobenzoic acid as a byproduct. So we have this compound is metachlorobenzoic acid or MCPBA, one of the most common epoxidation reagent we use in organic synthesis. Let's take a look again at the structure of MCPBA. So as you can see in this structure, we have three oxygen. So one oxygen of the CO double bond, one oxygen of the OH, and one oxygen between CO double bond and OH. So we have three oxygen. So the structure with three oxygens, we call that percarboxylic acid. Particularly in this case, we have metachloroperbenzoic acid. With the byproduct, so in the byproduct, we see that we have just two oxygens, one oxygen of the CO double bond, and the other oxygen of the OH group. So with this structure, we have the carboxylic acid, or in this case, we have metachlorobenzoic acid. So this is the difference between percarboxylic acid and carboxylic acid. So 3 oxygen for percarboxylic acid and 2 oxygen for the normal carboxylic acid. Let's talk about the mechanism for epoxidation reaction. So we have the reaction between cyclohexene and metachloroperbenzoic acid, MCPBA. So we're gonna have the nucleophilic attack from the double bond to the oxygen connected to the hydrogen. The single bond between oxygen and oxygen will be broken and the electron of the bond will move here. Then the CO double bond will attack the hydrogen of the OH bond, and the OH bond will re-attack to the double bond of the cyclohexene. So we're gonna form the epoxide as the main product of the reaction. And for the two hydrogens, they will end up being in the same side of the molecule because the double bond is a flat molecule. So the reaction can either happen at the bottom or at the top of the double bond. And we're gonna form the mixture of the two products. And we have metachlorobenzoic acid as a byproduct. So what will the geometry of the epoxide be when we start with different alkenes? So first, let's talk about the cis alkene. Alright, with the cis alkene, we have the two hydrogen being in the same side of the double bond. So this cis alkene react with MCPBA. We're gonna form the cis epoxide. Alright, so with the cis epoxide, we have the two methyl will be in the same side of the epoxide. And the two hydrogen will be in another side of the epoxide. So if we start with a cis alkene, we end up with a cis epoxide. And if we have a trans alkene, so this is the trans alkenes because the two hydrogen be in the opposite side of the double bond. So the trans alkene react with a MCPPA. We're gonna have the trans epoxide. So we have the two methods will be in the opposite side of the epoxide, and we have the same situation for the two halogen. So the two halogen will be in the opposite side of the epoxide. So if we start with a trans alkene, we end up with the trans epoxide as well. So the geometry of the epoxidation product will be dictated by the geometry of the starting material. If we start with 6 alkene, we form the 6 epoxide, and if we start with a trans alkene, we end up with a trans epoxide. We also form the enantiomer as well, because again the double bond is a flat structure, so the reaction can either happen at the top or at the bottom of the double bond, and we're gonna end up with the mixture of two products, the mixture of two enantiomers. Again, we have this is epoxide for the top reaction and the trans epoxide for the bottom reaction. In today's experiment, you're gonna react the cyclohexene with MCPPA. But first, let's talk about the safety of the experiment. MCPPA is shock sensitive, so do not grind or it could explode. Cyclohexene stinks, so you need to work in the hood and keep cover when transporting. Right, so when you move between the balance area to your hood, when getting the chemicals, you need to keep covered the container. Epoxides are irritants, so try to avoid skin and clothing contact. Moving on to the procedure. So first, you need to gather the stir bar, the MCPBA, and the methylene chloride. And then you're gonna add the cyclohexene. Make sure that you add the chemicals in this order, otherwise the reaction doesn't work. Next, you're gonna stir the resin vigorously at room temperature for about 45 to 60 minutes. Then wash the resin mixture with sodium bicarbonate to remove the carboxylic acid byproduct. Repeat this step 3 times in order to fully remove the byproduct. Then you're gonna wash the resin mixture with sodium bisulfite again 3 times to fully remove the unreacted MCPBA. Then wash the resin mixture with sodium chloride to remove the inorganic impurity. Then dry the organic layer with anhydrous sodium sulfate. Then remove solvent by the rotowap. When you get the final product, you need to characterize the product using FTIR and proton NMR. And that's it for today's video.